Well, unfortunately, we now come to the final presentation for today and also for the event. With advanced simulation technology, Moldex3D enables precise analysis and prediction of process flows to have a faster product development and less material waste. Thanks to Cindy and thanks to Ray Wu, who's giving us a better understanding of optimizing a multi-circularity mold for medical device manufacturing.
Okay, hello everyone. We are Moldex3D, and we were talking about a topic a little bit different from what you have heard in this series, because we are only focused on the design and manufacture of the part itself. And we are Moldex3D, so firstly we introduce ourselves, and then after that we will show how can we help in the medical industry for sustainability with the CAE software. And after that, we will have two case studies, have a closer look how could our software help our users to resolve their issues during the production. Yeah. Okay, so about us, we are one of the world leading provider for the plastic simulation software. And we founded in 1995, so it's already around 30 years. I think next year will be our 30 years anniversary. Yeah, and our goal is to help our customer to have a low cost, to lower the cost, the effort and investment when during the mold design stage and also the mold manufacturing stage. And also with the reduce of the mold trial and also the production trial, we can help our user to make the production become more environmental friendly. And also we can help the users to minimize, for example, the design cycle time, and then it can reduce your time for the product directly to the market. Okay. So here is the picture that explains how do we help. Firstly, you usually have the part and mold design, and then after that, in the past, we usually go to the tool making, and then go back to the iteration if the mold is not really suitable. And yeah, with the CAE validation, you do not get into the tool making directly. That means you are saving the mold modification cost and also the waste that generated by the tool modification. And you simply run on the simulation, and since electricity is relatively sustainable, more than the modification in the tool. And then we can use this to help our users to reduce the waste. Okay, and other than that, we introduce ourselves about where we're from. So here is Taiwan, a tiny island beside China. I guess most of you are familiar with the name a lot during these few years. Yeah, and we are located in here, Hsinchu, and yeah, me and Cindy are most of our time is in Hsinchu, and we also have a lot of sites. Also, we have one site in Netherlands in Utrecht, and also other sites around the world. And we have around 300 employees dedicated only for injection molding simulation. So you can count on us on if you have any questions regarding the injection molding. Yeah. Here is our customers. They are located in mostly Europe, like SHL Medical, Nolato Meditech, Coloplast, Sartorius. Maybe these are familiar for you, and some of you are also our customer, like I think Belda Medical and Ritter GmbH. Yeah, they are our customer. Yeah. Okay. Okay, so let's get into the topic. How can we help? Because right now we are having a growing demand in plastic for medical products because it's clean, and since the request is growing, then you will have an increase in the production. Then, of course, when you are modifying the tool, there will be a lot of waste, and also when you are doing the mold trial, the plastic you spend to make the plastic part maybe not reusable, or maybe it's reusable but not acquiring your standard, so you need to dispose them, and we can decrease that part of the waste. Yeah. So that's why Moldex3D can help in the sustainability. Okay, so yeah, here is two directions that we can do. First is reduce the cost. We can reduce the human power since there is more and more tool for automation in our simulation. And so you can reduce the time spent maybe in design of the part. Of course, selection of the material is still, yeah, depends on your knowledge, something like that. And we can also help to do the optimization of the process itself before you get into the machine. So for example, Angle also have a device can help you out to optimize the process. And if you can get a closer process before you get into the machine, then you will have less iteration maybe in the Angle machine. Yeah. Also, together with these two, we can reduce the time to market for your product. And also, there's a lot of you maybe are using the hot runner system to reduce the waste from the cold runner. And we also have a specialized module that can simulate the behavior of a hot runner system and address the issue maybe happen in the hot runner system and help you to fix the production problem. And later we have a dedicated case for that topic. Yeah. Okay. Okay, so yeah, in general, we can help in the product design, mold design, and process setting with the simulation, and we can reduce the trial and error in the typical way with the simulation, and yeah, that's what we can help. Okay, so here are some topics that we usually faced during the medical part production. So, for example, it is hard to, because usually the shape of the medical part are really special with some dedicated design. So there are some small draft angles might affect the ejection behavior during the production, and we can use some simulation to help you. Also, there will be a lot of production. You met the problem with air trap or bubble, or the flow bath in the multi-cavity mode. And these are the topics that usually our customer in medical part would face. And we have some solutions for you. So for example, for a small draft angle and air trap and bubble, we have here, the multi-cavity mode analysis. You can put multiple cavity inside the simulation and see the flow behavior, the balance between them. And then you can decide, okay, maybe I should modify the gate size, maybe I should modify the part size, and then try to optimize everything and make sure the production is perfect before you really get it started. Yeah, so you can reduce the time for the mold trials. Okay, here is also more results that our customer will look into. For example, the roundness and residual stress and deformation. These are the things that maybe you cannot address directly with the observation. It's more like with the physics calculation. You can see the residual stress, how would they impact the quality of your part. And with the simulation software, you can directly see it. Yeah. Yeah, so, okay. Yeah, so we also have some tools to help you out on these topics. Yeah, so here, later on, Cindy will introduce two cases. We will focus on two topics. First one is the flow bands in the multi-cavity. And we will see how the different size in the multi-cavity mode would influence the flow behavior and how do we address the problem with the simulation software. So.
Okay. Thank you, Ray, for the introduction. And I don't want to take too much of your time, so I'll just jump directly into the two case studies that I would like to share today. So the first one is on the multi-cavity molds manufacturing, which Ray just mentioned about. And the second one will be on a more special case, which is a string issue with a hot tip design. This is something very special, not very related and seen commonly in the industry, but it's a case from one of our renowned customers that we think it's very interesting that we would like to share today. So the first one, I would like to talk about how our customer, Polyshot and Partner Cruise Analysis, use our software to optimize hot runner family mold manufacturing. And just to reference them a bit, thank you them for providing the analysis for us to share today. This first case is not only a multi-cavity mold, it's also a family mold with 4 different part sizes and 2 each. So you can see that there's the smallest part here with 19 grams and then 22 grams, 23 grams, and 26 grams. They are all of same wall thickness, 1.5 millimeters, same gate size, and very similar generic features. So today, we will not be talking about maybe shear heating issue causing the imbalance in the runner. We will be talking about the unbalanced flow because of the different part sizes. So I think this is quite intuitive. You can imagine that you have different part sizes in the mold, then the smallest part may be filled first. As you can see from the left-hand side, at 90% filling stage, some of the cavity is still not yet filled, but some is already fully filled. And this unbalanced fill behavior can also be seen through the filling sprue pressure XY curve, which I will talk a little bit more about later. So with this case study, they ran a simulation with our software, and you can see that at 90% filling stage, the first smallest parts are filled first, and from the filling sprue pressure, you can observe also a pressure jump when the first parts are filled. So it's also quite obvious. We go a bit further. At 93% filled, the second parts are filled, and again, we see a pressure jump. And 99%, the third heaviest parts are filled again, and we see a third smaller pressure jump, but still a pressure jump. So every time the cavity is filled, you observe a pressure jump, which not only indicates a potential part quality issue, but this also means that energy consumption, energy requirements will be larger for these kind of increasing injection pressure required because of increasing clamping force required too. And finally, in the end, the largest part are filled, but you can see from the pressure results, there's a large difference between all different part sizes. The pressure are unbalanced, the filling patterns were unbalanced, and this can lead to potential issue, as you can expect it, maybe different deformation defects for different parts because some are filled at a lower pressure, some are filled at a higher pressure. Or maybe some flash issue may be occurring in the first parts that's filled because of the overpressurized cavity. So this kind of issue, we would definitely want to avoid, and we don't want it to happen. So then how can we solve this problem? And it's quite intuitive. If you have a bit of experience in injection molding, and all the tool engineers may know that we can modify the runner size, the gate size. But so for the smaller parts, we can reduce the runner and gate diameter. For the larger parts, we can increase the runner and gate diameters. But how should we optimize, and what is the optimal diameters that we should use? So as Ray just mentioned, in traditional trial and errors, you may have to create a new mold and then do a mold tryout again, and then shoot a part and check the dimensions if they are okay. But every time you do a mold tryout, it's a new mold that has to be created. It's more material has to be injected, and that's more waste, that's more cost, and that's less efficient. So All of these can also be done in the simulation. So the iterative process, you can create a new model, run a simulation, and check the results. And with this case, many iterative process, they also find the optimal parameters. So you can see that at 99% filling percentage, finally, all the parts are not yet filled, so there's a small gap for each part that's not filled yet. And the pressure distribution among all the different parts are also quite even, which helps solve the issue. Yeah, and coming back to the sprue pressure curve, you can see that with the original unbalanced field, there's a large increase because of a lot of pressure spikes, pressure jumps. The maximum pressure was at 108 megapascal, and after we reached the balanced flow, the maximum pressure had dropped down to 73 megapascal. So this not only solves the poor quality issue that may potentially occur, but it definitely help reduce energy consumption. So from the pressure decrease around 72%, we can imagine that from the original, maybe the head of the injection process, the beginning of the injection process, that's even more energy savings from the reduction of injection pressure. So that was the first case. I will conclude everything in the end. So I'll just jump very quickly to the second case. So this is a case with the string issue with the hot tip design. So the model is using a hot runner tip like this kind, which is, I think, quite typical hot runner design in the industry. Just a disclaimer, this is from a customer, one of our renowned customer who shared this case, but because of the confidentiality, everything I share later, it's modified. So, but it's very interesting, so I would just like to show you, and I think it suits the purpose of showing you all the problems and how they solve this issue. So this is a hot runner connected to a cold runner model, and you can see that the hot runner tip is extended slightly into the cold runner. So this is probably very typical, so everything seems to be fine. But then, oops. With this model, they observe a string issue at the top of the cold runner when being ejected. I can't show a picture here, but this is a string of melt being pulled out of the cold runner after being ejected. So from our customer, they were saying that the tool department came to their CAE department. They are telling them, oh, they have this issue that has to be solved. And at the first thinking, you may think, okay, we would need to solve this issue. But then if you think deeper, actually, this is a very tiny issue, very cliche, because cold runner will be probably post-process, removed or recycled afterwards. So why should I even take time to solve this small issue? Like this, why do you need me to solve it? It's so tiny. But for them, they said that, okay, their end customers, or who they are providing the tool, just cannot accept this tool. For them, they think that this is a tool that's not fitting their criteria. So they are Japanese, they cannot accept this. And this is talking about a deal order of a few $1 million. So, okay, they have to solve this issue. Even though it's tiny, they have to do it. Yeah. So very intuitively, they think of, okay, probably it's this hot, sharp tip that's causing this issue. So if they cut off the tip, they can probably fix this issue. But how can they prove it to the tool engineers? So the tool engineers told them, you need some evidence. What if I cut this out, but it's not solving the issues? It's more cost again. So they came to Moldex3D and ran a simulation with our software. And you can see that with the original design, there's a large increase in the shear rate just very close to the tip area. And with the modified design, the shear rate is a lot lower. So this gives them some evidence that it's probably because of the high shear rate near the tip that's causing probably a higher temperature increase. So then they went and looked deeper to the temperature distribution. For this case, it was quite interesting because during the packing stage, it was actually a lot higher increase in the temperature because of the high holding pressure required. So during the filling stage, the temperature increased because of the high shear rate. And at the packing stage, it increases even more for this case. And they look at the molten core results. So this is a material with around 142 freezing temperature. So we have the molten core results at end of cooling, and you can see very clearly for the original design, there's a connected molten core that's not fully cooled down yet. So probably that's causing the issue. And with the modified design, you can see clearly that there's a disconnected molten melt in the area. So this helped them to be more confident and tell the engineer that, okay, you can modify the tool, you can check, this is probably the reason. They went and modified the tool, and according to them, it actually solves the issue. So that was very interesting to us. We never seen this kind of case. So so that's something that we think that's very interesting. We would like to share with you. So a bit of a conclusion. I think with all the above mentioned reasons, you can see that with simulations, we can not only predict potential problems with simulations, we can also solve the problem by optimizing parameters during the product design stage, the mold design stage, also the manufacturing process. Today, the cases I've shown is mostly on mold design stage. But of course, during part design stage, you can also check, for example, deformation defects and modify the part thickness, modify the ribs or bosses. During the manufacturing process stage, you can also optimize processes like filling time, packing time, to optimize for better part quality. We can also validate design ideas through simulations. So like the second case we show, many engineers, they actually have the experience and knowledge already, but can they validate, can they prove their thoughts? We think simulation is really a great tool that helps our customer to see through the cavity, so see something that with simulation, what's happening in the cavity. Yeah, so with simulation, we can also help reduce traditional trials and errors, like Ray just mentioned. So all the mold tryouts that you have to do in reality, that can be greatly reduced. I wouldn't say you can 100% disregard mold tryouts. That's probably not possible, but I believe that simulation can greatly reduce the number of tryouts that's needed. So that's definitely reduce cost, waste, and time to market. If you think of the material, the molds that you have to make, during the mold tryouts. So wrapping up and coming back to our topic of sustainability these 2 days, we believe that with simulation software, we can definitely help the medical industry to become more sustainable in the future or starting from now. Yeah, thank you. So these are our contacts.